So in this lesson, we're going to compile everything we know about the second family of functions, the exponentials. And we study exponential functions in depth, or in more depth, in Chapter 4 after we do the linears. So let's put together everything we know about the exponentials. So first off, we studied them first. They were actually the very first thing we looked at in sequences because these were the ones that were based on the fractals or the geometric sequences. And just like the arithmetic sequences, geometric sequences are exponential functions, but they have a domain that has been limited to only the natural numbers. So I plug in the numbers 1, 2, 3, 4, and I can generate my geometric sequence by the common ratio. Remember, that was that multiplier that created those numbers. And they had apparent formulas that were a sub n equals a sub 1 times r to the n minus 1. Because remember, we talked about how the repeated multiplication translated to an exponent, which is why these are called exponential functions, because the variable is in the position of the exponent on the term. And then we moved on to big graphs in class, and we noticed a couple of things about them. Now in class I said the parent was y equals 2 to the x, and that's not actually true. It's actually y equals some constant like a 2 or a 3 or a 4 or a 10 or whatever raised to the x power. And I'm going to just put in parentheses y equals 2 to the x because that's the one that I made everyone graph in their big graphs. And the graphs of these all had the same shape, and the name wasn't very helpful. It was just an exponential curve. And they basically looked like this, and they were, or they could be decreasing like that, or they could be reflections of this, of one of these two, like through an x-axis, so flipped upside down. And their equations, and the ones we looked at, were of the form y equals that number, remember where the number was where x equals 1, times that common ratio that we had before to the x minus 1 power. And then we changed it slightly, and we said it could be like this, where we could add something at the end. So it's that a, which is like the same as the number there, the b, which is the common ratio, and the plus c, because I can shift it up or down by adding or subtracting something. I can do that for all of the graphs. And then we talked about domains and ranges when we discussed them as functions. And they are functions because they do pass the vertical line test, and their domains were all reals. And that's actually true for all of the families of functions that we study in Algebra 1. They all have domains that are all real numbers. But the ranges were different. The ranges were y is less than or y is greater than some number. And that number we talked about as being where the asymptote was on the graph. Because remember, these graphs have values at some point that approach some imaginary line, and we draw them in here. So they approach some imaginary line that we're going to call the asymptote, because remember, the asymptote is a line that a graph will get really, really close to but never cross over. And when you were making your tables to graph your exponentials, you notice that there'd be a value that would get really, 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 really close to. And that's how I determine what the range is in terms of what it's less than or greater than. And for the less than ones, remember the asymptote was above the curve, and when it's greater than, the asymptote was below the curve. And so that's how I would find the range. And remember, it was strictly less than or strictly greater than because we could never find a value of x that would zero it out to hit that value. And then after that, we talked about transformations, and we didn't spend very much time on the transformations for exponentials because we really didn't have to. So for the transformations, all we needed were to move them around a bit. So if I said f of x was just some exponential function, if I wanted to move the graph up or down, I would have to take the function rule and add some number to it to move it up, and I can add a negative number to move it down or subtract a number to move it down. The left or right shifting was exactly the same. I would have to, instead of adding something wherever the x was, I would have to replace it with x plus or minus some number to move it left or right. And in terms of increasing or decreasing, that was actually different. If I wanted to make this function increase or decrease, and increase meant it was growing like this, and decrease meant it was going down like that. Those had to do with the common ratio. So for this graph, the ratio, or that multiplier, had to be greater than 1. And for this graph, the ratio had to be between 0 and 1. And it couldn't be 0 because that wouldn't be exponential, and it can't be 1 because that wouldn't be exponential. And they could never be negative because the negatives cause signs to swap back and forth and it wouldn't generate that shape. And then this number also told me the steepness. The higher this number is, like if it's 2, 3, 4, 5, 6, 7, 8, 9, the faster it would grow. And so that's all I really needed to know for the transformations for exponential. So to recap everything, like I did with linear, geometric sequences belong to the exponential family. They just have a domain that's been limited to the natural numbers. The parent formula, a sub n equals a sub 1 times r to the n minus 1. The parent was some constant raised to the x power. The graphs had asymptotes and were exponential curves, either increasing or decreasing, or flips of these. The equations were, well, I just replaced the apparent formulas a sub 1 n and with x's and y's. And I can add on that plus c to move the graph up or down. The domains were always all reals. The ranges had to deal with the asymptote. So I had to figure out where the asymptote was, and if the graph was below it, the y values would be less than or equal to the asymptote. If the asymptote was below the graph, then I know that the y values are greater than the value of that asymptote. And then transformations, up or down, just add the quantity at the end, left or right, replace the x with a quantity that had addition or subtraction. And then if I wanted to be increasing, my ratio had to be greater than 1. If I wanted to be decreasing, my ratio had to be between 0 and 1. Oh, and I forgot one thing. If I want to reflect it through the x-axis, which means flip it upside down, I had to use the negative version of the rule. So I had to multiply it all by a negative. And that's everything we know about exponential. And in chapter 4, we'll learn even more.